Hello, today we're going to explore the fascinating relationship between linear equations and quadratic equations. By the end of this video, you will be able to visualize a quadratic equation as the product of two simple lines. Our main goal is to understand how the roots of a quadratic equation are directly connected to where the graph of the equation crosses the x-axis, and we'll do this by building a quadratic from scratch. Let's begin by defining two simple linear functions. Think of them as two straight lines. We'll call the first one L sub 1 of x, and we'll set it equal to x minus some number, which we'll call r1. And we'll call the second one L sub 2 of x, and set it equal to x minus another number, er2. Let's visualize these. Imagine a coordinate plane with an x and a y-axis. The first line, L sub 1, will cross the x-axis at the point r1, 0. Let's place a point on the x-axis at r1 and draw our first line. This line has a positive slope, and its x-intercept is r1. Similarly, the second line, L sub 2, will cross the x-axis at the point er2. How? Let's place a point on the x-axis at r2 and draw our second line, L sub 2. It also has a positive slope, and its x-intercept is r2. So we have two lines, each crossing the x-axis at a specific point. Our objective for this scene was to define and visualize these lines, which we have now done. Now here's the magic. What happens if we multiply these two linear functions together? Let's create a new function, q of x, by taking the product of L1 of x and L2 of x. If we expand this out, let's see what we get. Using the distributive property, or FOIL, we have x times x, which is x squared. X times negative r2, negative 1 times x. And finally, negative er1 times negative r2, which is positive r1, r2. Factoring out x from the middle two terms, we get x squared minus the sum of r1 and r2 times x plus the product r1, r2. Does this look familiar? It's a quadratic equation. This confirms our main idea. A quadratic equation is the product of two linear equations. In this scene, we successfully showed that multiplying two linear functions creates a quadratic function. This provides a new way to think about where these types of equations come from. Now let's examine the behavior of this new function. Q of x equals the product of our two lines. Where does this new function q of x equal 0? Remember, the x-intercepts of any graph are the points where the function's value is 0. So, we're looking for the roots of our new quadratic equation. For the product of two numbers to be 0, at least one of the numbers must be 0. So we need either L sub 1 of x to be 0 or L sub 2 of x to be 0. Let's check the first case. When does x minus r1 equal 0? This happens when x equals r1. So x equals r1 is one of our roots. What about the second case? When does x minus r2 equal 0? This happens when x equals r2. So x equals r2 is our other root. This gives us a monumental insight. The roots of the quadratic equation q of x are the very same values, r1 and r2, that were the x-intercepts of our original two lines. Let me say that again. The x-intercepts of the two lines we multiplied are the roots of the quadratic we created. This connects the algebra of finding roots to the geometry of graph intercepts. Our objective was to see why the roots of the quadratic appear where they do. And we've accomplished this by showing they come directly from the zeros of the component linear equations. Now that we know where the parabola crosses the x-axis, let's figure out what it looks like in between and outside of these points. Imagine our coordinate plane again, with our two lines L1 and L2 and their x-intercepts R1 and R2. Let's assume, just for this example, that R1 is smaller than R2. We know the parabola crosses at x equals r1 and x equals r2. What happens between them? Let's pick any x value between r1 and r2. Notice what happens with our lines. The line L1 of x is above the x-axis, which means the value of x minus r1 is positive. The line L2 of x is below the x-axis, so the value of x minus r2 is negative. Our quadratic q of x is the product of these two values. A positive number multiplied by a negative number gives a negative number. This means that for any x between r1 and r2, the value of the quadratic is negative. Geometrically, This means the parabola must dip down and lie below the x-axis in the interval between r1 and r2. So, we've now figured out the middle section of our parabola by using the signs of the two component lines. The objective here was to determine the shape of the parabola between the roots, which we achieved by multiplying the signs of the two linear factors. We've handled the space between the roots. What about the regions outside of them? Let's check there. Again, here are our lines, L1 and L2, with intercepts at R1 and R2. First, let's look at the region to the left of R1. Let's pick an x value that is less than R1. For this x value, notice that both line L1 and line L2 are below the x-axis. This means that both x minus R1 and x minus R2 are negative numbers. So our quadratic q of x is the product of two negative numbers. And what's a negative times a negative? It's a positive. This tells us that to the left of R1, the parabola must be above the x-axis. Now what about the region to the right of R2? Let's pick an x value that is greater than R2. In this region, both line L1 and line L2 are above the x-axis. Therefore, the values of x minus R1 and x minus R2 are both positive numbers. Our quadratic q of x is the product of two positive numbers, which is also positive. This means that to the right of R2, the parabola must also be above the x-axis. We can now complete our sketch of the parabola. We see that it opens upwards. We've now met our objective for this scene, which was to determine the sign of the parabola outside its roots by analyzing the signs of the two linear factors. So far, we've looked at what happens when our two linear functions or factors have two different roots, R1 and R2. But what if the roots are the same? That is, what if our two lines are actually the same line? In this special case, R1 equals R2. Let's just call this common root R. Our quadratic equation q of x now becomes x minus r times x minus r, which simplifies to x minus r all squared. This is a perfect square trinomial. Let's analyze this function. It's the product of a value with itself. First, when does q of x equal 0? It only happens when the base, x minus r, is 0. This only happens at x equals r. So the function has only one unique root, r. Now, what about the sign of q of x everywhere else? What is the sign of any number that is squared? A squared number is always positive, unless the original number was 0. For any value of x that is not equal to r, the term x minus r will be non-zero. And squaring a non-zero number always gives a positive result. So, q of x is positive for all x except x equals r. Let's graph this. The parabola only touches the x-axis at the point r0. Everywhere else, it's above the x-axis. It doesn't cross. The x-axis is tangent to the parabola at this single point. So, our objective for this scene was to analyze the special case of one unique root and see how it results in the parabola touching, but not crossing, the x-axis. Let's summarize what we've discovered today. We found that by starting with two simple lines, we can construct the graph of a parabola. The roots of the quadratic equation are the x-intercepts of the two lines we multiplied together. The shape of the parabola, whether it goes up or down between the roots, is determined by multiplying the signs of those two lines. When there are two distinct roots, the parabola crosses the axis twice. When there is one unique root, the parabola just touches the axis at that single point. This visualization connects the algebra of quadratic functions to their geometric graph in a powerful way. I hope you now feel more comfortable understanding how quadratic parabolas are built and how their roots behave. Thank you for watching.